Imagine standing at the edge of a vast churning ocean, not of water though, but of data, billions and billions of bytes flowing, shaping pretty much every aspect of our world. How do you become the skilled navigator of this immense digital sea? How do you not just survive, but thrive, innovate, and lead in this constantly evolving information landscape? That's precisely what we're here to unravel today on the Deep Dive. And if you're charting a course for career success in the digital era, or maybe just want to feel truly informed, we'll definitely hit that like, subscribe, and share button. Staying connected means you'll always have a shortcut to critical insights and readiness for what's coming next in the tech world. Our mission today is to take a truly deep dive into the foundational principles and also the cutting-edge ones of information systems. We're uncovering how data is managed, structured, and really leveraged across businesses. We'll extract the most important nuggets of knowledge to equip you, whether you're a student or maybe an early career professional, with the insights you need to understand, apply, and ultimately lead in this critical field.
Yeah, and we'll explore how information systems really form the very backbone of modern organizations. It's fundamental. This means looking at, well, everything, from the intricate architecture that keeps data flowing smoothly to the various ways we model and manage it, and even the crucial strategies for ensuring its quality and availability, especially in an always-on world. Understanding not just what these systems are, but why they matter for strategic decision-making, for innovation, that's absolutely key to your professional growth and, frankly, your leadership potential.
Okay, let's dive in. Data isn't just, numbers in a spreadsheet anymore, is it? It's the multimedia you stream, the biometric scans protecting your devices, the geographical information powering your maps, and even the health metrics from your wearables, like a Fitbit or an Apple Watch. It's truly ubiquitous. This incredible variety and just sheer volume of data is exactly what makes understanding information systems so vital today.
It really is. And what's truly foundational here is how all this diverse data connects back to critical business operations. Take a simple purchase order system, for instance. A really common example. You have data on product number, name, color, things like that. You have data on suppliers, their name, address, maybe a supplier number, and then data on the purchase orders themselves, a unique reference, a date. And these are all intricately interconnected, right? A product can be supplied by many suppliers. A purchase order is linked to one specific supplier. Or think about a modern taxi service, like the Sober example in our sources. They're tracking car owners, ride details, customer requests, all needing structured storage and retrieval. So at its core, a database is simply a collection of these related data items, all within a specific business process. It's designed for a target group of users and applications, maybe an inventory manager making sure stock levels are right, or perhaps a product manager monitoring sales trends.
It's almost hard to imagine business without databases now. But as you said, that wasn't always the case. What were the significant hurdles? What problems were businesses facing before this structured, database-driven approach really became the norm?
Oh, historically, businesses often relied on what we call a file-based approach. Just imagine each application, say payroll, inventory, customer service, using its own separate set of data files, completely siloed. And this led to a whole cascade of problems that severely hampered efficiency and, well, growth. First, there was rampant data redundancy, massive amounts of it. If customer details were needed by sales, marketing, and accounting, each department might just keep its own file, leading to huge duplication, wasted storage.
Right, like having the same customer address stored slightly differently in 3 different places.
Exactly. And that directly caused a high risk of inconsistent data. If a customer's address was updated in the sales file, but maybe not in the marketing file, you'd end up with conflicting information. That causes confusion, errors, definitely poor customer experience. Yeah. And another huge issue was the strong coupling between applications and data. They were tightly bound. So a structural change in one data file meant you had to go back and modify every single application that used it. Maintenance became incredibly costly and time-consuming.
Ouch.
And then there's concurrency control, or rather, the lack of it. When multiple users or applications tried to access and modify data simultaneously without proper mechanisms, you could easily end up with corrupted or inconsistent data. Imagine 2 people trying to update the same stock level at the exact same moment. Chaos.
Yeah, I can see how that wouldn't work.
Finally, integrating these siloed applications for cross-company services, like just trying to get a single unified view of a customer, became incredibly difficult and really expensive. And honestly, many firms still struggle with legacy file-based systems today. It's a persistent problem. The database management system, or DBMS, emerged as the revolutionary solution. It brought order, consistency, and efficient concurrent access to this data chaos. It drastically improved data independence, separating the data from the applications, and just made data management so much better. For good.
Okay, so if I'm interacting with, well, pretty much any application today that uses a database, ordering coffee, checking my bank balance, streaming a movie, there's a phenomenal amount of work happening behind the scenes. Let's delve into the brain behind the data. Our source material gives us a really detailed look at the internal architecture of DBMS. It sounds like a complex ecosystem of interacting modules.
Absolutely. And for anyone aspiring to design, build, or manage information systems, understanding these components is vital. It's about going beyond simply using the software to truly understanding how it works. That's the key difference. So at the highest level, the DBMS provides interfaces for various types of interaction. You've got data definition language, or DDL, statements for defining the structure. You have interactive queries, like typing SQL into a command line, direct application calls, where software talks to the database, and specialized database tools for things like administration or reporting. Inside, though, a sophisticated set of components orchestrates everything.
Okay, break it down for us. What are the main players inside this DBMS brain?
Right. First, we have the connection manager and the security manager. Think of them as the database's security team and maybe the reception desk. They handle who gets an authentication. They check what they're allowed to do authorization. This ensures only the right people can access specific data and perform specific operations. It's the first line of defense for security and compliance.
Makes sense. Security first.
Then there's the DDL compiler. This component processes those data definition language statements we mentioned. So when you define a table, its columns, the data types for those columns, the relationships between tables, that's the DDL compiler at work. It's essentially building the database's blueprint or schema, ensuring the structure is logical and consistent.
Got it. The blueprint builder.
Next, the database utilities. These are like the system's maintenance crew. Absolutely crucial for ongoing health and performance. They include tools for loading data from external sources, maybe spreadsheets or other files, reorganization utilities to optimize the storage layout for better speed, performance monitoring tools that report critical KPIs like how fast queries are running, user management for creating accounts and setting privileges, and maybe most critically, robust backup and recovery utilities. These safeguard against data loss and enable quick restoration if something goes wrong, like a hardware failure.
Backup and recovery, definitely don't want to forget those.
Definitely not. Then we get to the query processor. This is where the real magic of data retrieval happens. It's actually made up of several parts. A DML compiler for handling data manipulation requests. A query parser that checks the syntax of your query, make sure you typed it right. A query rewriter that might simplify or optimize the query logically. Then the crucial query optimizer. This component determines the most efficient way to physically execute the query. It looks at indexes, table sizes, and figures out the best plan, often using heuristics or rules of thumb. And finally, a query executor that actually carries out the chosen plan.
So the query optimizer is key. It decides how to get the data.
Exactly. And the single most powerful takeaway here is that a declarative language like SQL lets you specify what data you need. You say, get me customers in California, and the query processor, specifically the optimizer, intelligently figures out the most efficient way to get it. You don't need to tell it how to scan tables or use indexes. That abstraction is an enormous productivity gain for developers and users.
That is powerful. Hides a lot of complexity.
Immense complexity. Finally, we have the storage manager. This is the guardian of data integrity and concurrent operations. It directly interfaces with the raw data on the disk drives. This complex subsystem includes several key parts. First, the transaction manager. It supervises database transactions. These are sequences of read or write operations treated as a single atomic unit. All or nothing. It creates schedules for interleaved operations from multiple users to boost efficiency, and crucially, it guarantees those AACSB properties we mentioned: atomicity, consistency, isolation, durability.
He said, got it.
It commits successful transactions, making them permanent, and rolls back unsuccessful ones to prevent inconsistent data. Then there's the buffer manager. This component manages the transfer of data between the faster main memory, RAM, and the slower disk storage. It tries to keep frequently used data in memory to minimize slow disk I/O.
So it's like a cache manager.
Essentially, yes. A very sophisticated one for database pages. We also have the lock manager. It handles concurrency control. When multiple users try to access or modify the same data simultaneously, the lock manager uses locks to prevent conflicts and ensure data integrity. And finally, the recovery manager. This system supervises the correct execution of transactions and keeps a detailed log file of absolutely all operations. If there's a system crash, the recovery manager steps in. It uses the log file to undo any aborted actions or recover the database to the last consistent state, ensuring data consistency even after failures.
Wow, that is incredibly intricate. There's so much happening under the hood.
Yeah.
So let's connect this back. For someone managing a team or maybe architecting an IT system or even an early career professional looking to specialize, why is understanding these deep internal workings so important for their career growth? Sounds very technical.
That's a really great question because it might
Hmm.
seem like overkill, right? But this depth of knowledge provides a significant advantage that goes way beyond just using a tool. It empowers you to design more robust, more scalable, and more secure information systems right from the ground up. You can troubleshoot performance issues far more effectively. If queries are slow, you understand it might be the optimizer, or maybe locking issues handled by the lock manager, or perhaps buffer pool tuning related to the buffer manager.
So you know where to look.
Exactly. You grasp the why behind system behaviors. This enables you to make informed decisions about technology choices, about configuration settings, about hardware provisioning. For example, if your sober taxi app is experiencing slow ride confirmations during peak hours, knowing about the lock manager's role helps you diagnose potential concurrency bottlenecks. Maybe queries are waiting too long for locks. It's really the difference between merely operating a system and truly mastering it. Mastering it allows you to build powerful, resilient solutions that drive significant business value. And that ability makes you an invaluable asset, especially if you're aiming for leadership roles within IS. You can guide technical decisions with real understanding.
Okay, that makes perfect sense.
Yeah.
It's about deeper understanding leading to better design and problem solving. Now, before we even think about building the database itself, we need that blueprint. We talk about a conceptual model of our data. This is where data modeling comes in. It's like an architect sketching out a building before laying a single brick. Let's start with the classic, the entity relationship, or ER model.
Right, the ER model.
Yeah.
Formalized by Peter Chen back in 1976, it remains incredibly popular for conceptual data modeling. And a big reason is its intuitive and, frankly, user-friendly graphical notation. It really helps translate complex business requirements into a clear data structure that both technical and non-technical people can often understand. Its core building blocks are pretty straightforward. First, entity types. These represent the real-world objects or concepts we want to store data about, like a supplier or a product in our purchase order system example. Visually, we usually draw these as rectangles.
Like nouns, basically.
Kind of, yeah, the key things you're tracking. Then attribute types. These are the characteristics or properties of an entity. A supplier entity might have attributes like SUPNR, a unique supplier number, status, maybe date of birth. These are typically shown as ellipses connected to their entity type rectangle.
The details about the nouns.
Exactly. And finally, relationship types. These describe how entities are connected or how they interact. In our purchase order example, a supplier might supply products, or a purchase order might be on order with a supplier. We typically use diamond shapes for these relationships, connecting the related entity rectangles. And crucially, these relationships have cardinalities, things like one-to-one, one-to-many, many-to-many. These tell us how many instances of one entity can relate to another. For example, one supplier supplies many products. That's key information.
The basic ER model seems quite intuitive for straightforward data structures. But, business reality often gets a lot more complicated than just simple suppliers and products. Are there limits to what ER can represent effectively, especially when you have more nuanced relationships or maybe hierarchies?
That's a great observation, and yes, the original ER model does have limitations when things get really complex. That's precisely why the enhanced ER or EER model was developed. It takes those basic building blocks, entities, attributes, relationships, and adds more power, more expressiveness. It allows for richer modeling of the complex relationships that are really common in today's intricate business environments. ER introduces three key additional modeling constructs. First, specialization generalization. This is huge. It allows us to model ISE relationships representing hierarchies or classifications. For example, a general human entity type could be generalized from more specific vegetarian and non-vegetarian subtypes. Each subtype is a human, so it inherits common characteristics like name or date of birth. But they can also have their own unique attributes or relationships. Maybe the vegetarian has a dietary restrictions attribute.
Like classes and subclasses in programming.
A very similar concept, yes. Or think about different types of employees, like engineers or managers. They could all inherit from a general employee supertype, but have their own specific attributes or roles. Second, ER introduces categorization. This is used when a subclass is derived from multiple superclasses that represent different entity types. The subclass selectively inherits attributes from the superclasses it belongs to. Imagine maybe a registered user category that could be either a customer or a supplier, inheriting different things depending on which it is.
Okay, that handles more complex overlaps.
Right. And third, aggregation. This is powerful when a relationship itself needs to participate in another relationship. It lets you treat a relationship instance as a higher-level conceptual object. For example, the relationship employee works on project could be aggregated into a single conceptual unit, and then that unit could itself be assigned to a supervisor or have attributes like start date.
Treating a relationship like an entity.
Essentially, yes. Encapsulating it. And we even see elements of this evolution reflected in scenarios like our sober taxi company example, if they were dealing with an old codactyl database. In those older systems, complex NM, many-to-many relationships, like between customers and cab rides, often had to be mapped using extra kind of clunky, dummy record types. ER provides much more direct, natural, and intuitive ways to represent these complex real-world scenarios compared to those older, more rigid database models. It's a big step up in modeling capability.
So let's bring it back to the person starting their career. Why should they bother with these abstract diagrams? EER sounds even more complex. Why invest time in conceptual modeling when you just want to, build something?
This is such a critical point because it can seem abstract, but good conceptual modeling is the first and arguably the most important step towards building a functional, efficient, and crucially maintainable database. It ensures that the data requirements are captured accurately and in a user-friendly way before you write a single line of code or create a single table. This prevents incredibly costly redesigns and refactoring later down the road. Finding a structural problem after the system is built is exponentially more expensive to fix.
Pay now or pay much more later.
Exactly. For your career, mastering conceptual modeling means you can effectively communicate. You can talk to non-technical business stakeholders using ER or EER diagrams to confirm you've understood their domain and requirements correctly, and you can communicate clearly with technical development teams, providing them with a solid blueprint. You're translating real-world problems into structured data solutions. It's a fundamental skill for any information systems professional. It bridges that gap between business needs and technical implementation. And honestly, it's a key differentiator for anyone aspiring to architectural or leadership roles.
Okay, bridging that gap is key. Now, beyond ER and ER diagrams, we can also look at another powerful modeling tool, the UML class diagram. This often comes up in object-oriented environments. How does this compare? Is it just another way to draw boxes and lines?
Well, it uses boxes and lines, yes, but the UML class diagram comes from the object-oriented world and offers a somewhat richer semantic perspective than ER in many ways, especially when you're designing not just the data structure, but also the behavior associated with that data. It uses classes, attributes, which are like variables, methods, which define operations or behavior, and associations, which are like relationships. It certainly supports concepts similar to ER, like specialization, generalization, inheritance, and aggregation, composition. UML models these robustly, often with more explicit notation borrowed from object-oriented programming concepts. You can clearly show how an employee class is a superclass for engineer and manager subclasses, showing inherited features.
So similar concepts, maybe just different notation.
Similar concepts, yes, but UML adds more, particularly around behavior and constraints. One really powerful feature is the Object Constraint Language, OCL. This allows you to define precise business rules or invariants that the data must follow directly within the model itself, not just in separate documentation. For instance, you could write an OCL constraint stating that a department must have at least 20 employees, or that an employee who is managed to be a department must have years employed 10.
Wow, embedding rules right in the diagram.
Exactly. This level of detail ensures business rules are captured formally and are less likely to be missed during implementation. It makes the model a much stronger tool for system specification. UML also offers more advanced modeling concepts like specifying changeability properties for attributes can be modified after creation, and different types of dependency relationships between classes.
The ability to bake in such detailed rules directly into the model, like with OCL, sounds incredibly valuable for building correct systems. So for a developing IT professional, maybe someone on a project team, how do you decide which modeling approach is right for a new system? Or even to understand diagrams they might encounter in existing systems. Is it ER or UML?
Right, connecting this to the bigger picture. The choice of modeling tool really depends heavily on the context, the complexity, and the nature of the system you're building. UML class diagrams are often preferred or even required in the context of object-oriented software development, where the system's behavior, the interactions between objects, are just as critical as the data structure itself. Think Java or C# development. ER or ER might be more common and perhaps a better starting point for purely data-centric applications like data warehouses or reporting databases, where the primary focus is on organizing and relating information, maybe less on complex object behavior.
So choose the tool that fits the job.
Precisely. For your career, being fluent in different modeling languages, understanding the strengths, the weaknesses, the typical use cases for ER, and UML makes you a much more versatile and invaluable asset. It allows you to analyze existing systems effectively, regardless of how they were modeled. It enables you to design new systems using the most appropriate approach. And it helps you manage complex information structures effectively. This ability to understand and apply different modeling paradigms is really a core leadership capability in IS. It allows you to guide teams in making the right architectural choices early on.
Fluency in multiple modeling languages, that makes a lot of sense. Be adaptable.
Okay.
Okay, so we've painstakingly crafted our data's blueprint using these conceptual models like ER or UML. But a blueprint is just a drawing until you actually build the structure, right? How do we take these conceptual models and bring them into the real world, into the actual databases and systems we use every single day?
That's exactly where the relational data model comes into play. It is, by far, the most widespread implementation model, forming the backbone of so many systems we rely on daily. Introduced by the brilliant E.F. Codd back in the 1970s, it really revolutionized data management by organizing data into relations, which we usually just call tables. These tables are composed of rows, or tuples, and columns, or attributes. Each relation, or table, has a defined set of attribute types, like supplier number is an integer, supplier name is a string, and crucial integrity rules are enforced through primary keys, one or more columns whose values uniquely identify each row in the table. No two suppliers can have the same supplier number, for example, and foreign keys. These are columns in one table that link to the primary key of another table, establishing and enforcing the relationships between them.
The links between the tables.
Exactly. Consider our purchase order example again. You'd have tables like supplier, product, then maybe a supplies table to handle the many-to-many relationship between them. Also purchase order and Pauline, the items on each order. In diagrams or documentation, you'll often see the primary keys underlined, like SUPNR in supplier. And foreign keys might be italicized or marked somehow, like SUPNR appearing in the supplies table, linking back to the supplier table. This structured approach, where each row tuple has atomic single values for each attribute, ensures data integrity and clarity. It's mathematically founded and very robust.
Okay, that structure sounds solid, but just putting data in tables isn't quite enough, is it? We often hear this term normalization bandied about in database circles. What exactly is that, and why is it considered so important for maintaining data integrity, especially over the long term?
You're right, just creating tables isn't the whole story. Normalization is a critical process, a formal technique, for analyzing relational models, the table structures themselves, to eliminate redundant data and, more importantly, to prevent various data anomalies. These are problems that can occur during insertion, deletion, or update operations if your tables aren't structured properly.
Anomalies. What kind of problems are we talking about?
Well, if a table isn't normalized, you can run into significant issues. Imagine an unnormalized supplies table where you store supplier details, like name and address, right alongside the product details for every product they supply. Okay, what could go wrong? First, a deletion anomaly. If you delete the last product supplied by a particular supplier, you might inadvertently delete the supplier's details entirely, even if they still exist as a supplier but currently supply nothing else in your list. You lose information unintentionally.
Ooh, that's bad.
Yeah. Second, an update anomaly. If a supplier changes their address, and that supplier appears multiple times in your unnormalized table, once for each product they supply, you have to find and update that address in every single row where that supplier appears. If you miss one, you now have inconsistent data. Very risky.
And hard to manage.
Very. Third, an insertion anomaly. Maybe you want to add a new supplier to your system, but they haven't supplied any products yet. In that badly designed table, you might not be able to insert the supplier's details because the product information fields would be empty, potentially violating key constraints. You can't add a supplier until they supply something, or vice versa.
So you can't store potentially valid information.
Exactly. Normalization is a step-by-step procedure with different normal forms, like first normal form, 1NF, second 2NF, third 3NF, and so on. It transforms these potentially problematic, unnormalized models into a set of related tables that are more efficient, more consistent, and less prone to these anomalies. It ensures data integrity, reduces redundancy, you store the supplier's address only once in the supplier table, and makes the database much, much easier to maintain and evolve over time. It's a foundational concept for designing robust and reliable relational databases.
Okay, normalization sounds essential for clean, reliable data. Now, how do we actually interact with these normalized relational databases? Let's talk about SQL, the structured query language. It's pretty much the universal language for talking to relational databases, right? And it feels like a skill everyone in tech, from developers to data analysts to even some business users, should have at least some grasp of. It's how you ask questions and get answers from your data.
Absolutely. SQL is incredibly versatile, and it serves two main purposes, often categorized as data definition language, DDL, and data manipulation language, DML. First, SQL DDL. This is how you define and manage the database structure itself, creating the blueprint in the actual database system. Commands like create are fundamental. You use create schema, create table, create domain for custom data types. For example, you'd use create table purchase order, and within that statement define PNR, purchase order number, as the primary key, ensuring each order has unique ID. You'd also define SUPNR, supplier number, as a foreign key that references the supplier table, establishing that crucial link between orders and suppliers.
So DDL builds the container.
Precisely. And you can specify powerful rules within DDL. For instance, when defining that foreign key, you can add on delete cascade. This means if you delete a supplier from the supplier table, the database will automatically delete all associated purchase order records linked to that supplier. That's a critical business rule decision you embed right in the structure.
Wow, that's powerful and potentially dangerous if not thought through.
Very true. You also have alter table to modify existing structures, add a column, change a data type, and drop table to remove structures entirely. Then you have SQL DML. This is for actually working with the data inside those structures once they're built. There are four main DML statements that form the core of data interaction. First and foremost, select. This retrieves data, and it is immensely powerful. You can do simple things like select prod name from product, where prod name like chard percent to find products whose names start with chard, but you can do so much more. You can use aggregate functions like count, SU, AVG, MIN max to summarize information, maybe calculate the average purchase price of products from a certain supplier.
Summarizing data on the fly.
Exactly. You can use group by Y to categorize results, like finding the average price per supplier and having to filter those grouped results, like only showing suppliers whose average price is above a certain threshold. You can use order by to sort the results. And very importantly, you can join data from multiple tables together. For instance, combining the supplier table and the supplies table based on their common SUPNR column using an inner join. This lets you see which specific supplier supplies which specific product, bringing related information together.
Joins seem fundamental to relational databases.
They are absolutely central. And you can even use nested queries, also called subqueries, to solve complex problems step by step, like finding the names of suppliers who can supply product 0178. You might first write a subquery to find the supplier numbers, SUPNR, from the supplies table for that product, and then use those numbers in an outer query to select the corresponding names from the supplier table.
Breaking down complex questions.
Right. The other three DML statements are simpler but essential. Insert adds new rows of data into a table. Update modifies existing data in one or more rows. And delete removes rows of data from a table.
Select, insert, update, delete. The core operations. Now, with all that valuable data neatly stored and accessible via SQL, security becomes absolutely paramount. This seems like a huge concern for any future IT leader or system architect. How does SQL handle security? How do you ensure that only authorized people can see or change specific data?
That's a crucial point, and SQL has robust mechanisms built in for security and access control. The core commands here are grant and revoke. You use grant to give specific privileges to specific users or roles. For example, you could grant select, insert, update, delete on supplier to B. Basins, giving a user named B. Bisons full rights to work with the supplier table.
Very specific permissions.
Exactly. Or you could be more granular. You could grant select, prod name, on product to public. This would allow everyone, public, to see only the product number and product name columns from the product table, effectively hiding potentially sensitive information like cost or inventory levels stored in other columns of the same table. This fine-grained control is absolutely essential for implementing robust data security policies and maintaining confidentiality and integrity. Revoke is simply the opposite. It takes away previously granted privileges.
So you have control at the table level and even the column level.
Yes. And furthermore, SQL supports other important concepts related to access and organization. Views. These are essentially saved, select queries that act like virtual tables. They don't store data themselves, but provide a controlled window onto the data in the underlying base tables. Views are part of the external data model and offer a critical layer of abstraction and security. You can define a view that only shows, say, active suppliers or products above a certain price point, and then grant users access to the view instead of the base tables. This simplifies queries for users and enforces security rules.
Hiding complexity and enforcing rules through views. Got it.
Right. And indexes. These are part of the internal data model closer to the physical storage. They aren't about security directly, but about performance. Think of them like the index in the back of a physical book. They don't change the book's content, but they provide pointers that help you find specific information, rows with certain values, much faster without scanning the entire table. Creating the right indexes is critical for query performance.
Okay, so really connecting this to the bigger picture for our listeners. Understanding SQL's power and its nuances, from defining schemas with DDL to manipulating data with DML to managing security with grant revoke, and views this is absolutely critical knowledge for any information systems professional, right?
Absolutely critical. It's not just a technical skill you learn once, it's a strategic one. It enables data-driven decision-making by allowing people to access and analyze information effectively. It helps ensure regulatory compliance through proper security controls. And it's fundamental for efficient application development, as most business applications need to interact with a database using SQL, whether directly or through an abstraction layer. Mastery of SQL and its various aspects really is a gateway to impactful roles in data management, application development, data analysis, and system architecture.
Makes perfect sense. It's the language of data for so many systems. Now, relational databases using SQL are fantastic for structured data, the kind that fits neatly into tables. They form the bedrock of so much of our digital world. But the world isn't always neatly organized into rows and columns, is it? What happens when your data is more complex, maybe more object-like from programming, or needs to store diverse, irregular structures? This seems like a limitation.
That's a very accurate observation. The rigid structure of relational tables can sometimes be limiting, especially when dealing with complex data types or trying to map directly from object-oriented programming languages. This led to the emergence of object-oriented database management systems, OODBMSs. Their goal was to directly store objects as they exist in programming languages, encapsulating both the data, attributes or variables, and the functionality, methods, or operations within a single database object. This was designed to solve the so-called impedance mismatch problem. That's the difficulty and awkwardness developers often face when trying to translate complex object structures from languages like Java or Python into flat relational tables and then back again.
So trying to make the database look more like the programming language objects.
Exactly. OODBMSs fully embrace key object-oriented concepts like encapsulation, bundling data and methods, inheritance, classes deriving properties from superclasses, polymorphism, objects taking many forms, and method overloading overwriting. And while ODBMSs do exist, systems like DB40 or Cache found some success in niche applications, for example, Delta Airlines reportedly used one to efficiently cache complex C++ objects for real-time airline crew rerouting. They haven't seen widespread mainstream adoption for general-purpose database use, largely due to their complexity, lack of a single standardized query language like SQL initially, and the massive existing investment in relational technology.
Interesting. So the pure object database didn't quite take over. But what's fascinating is how the database world then adapted by bringing some of those object-oriented features into the dominant relational databases. This led to object relational DBMSs or DBMS. These sound like a powerful hybrid, trying to get the best of both worlds. But does this hybrid approach maybe come with its own set of complexities, or is it a good compromise?
That's a fair question. The intention behind ORDBMS wasn't necessarily to be a perfect hybrid, but rather to extend the proven relational model to handle specific types of complexity more gracefully without forcing users to abandon the familiarity and power of SQL and the relational foundation. So ORDBMSs are essentially relational databases that have been extended with object-oriented features. They offer a compelling middle ground for certain kinds of problems. They allow for much richer data modeling than traditional RDBMs by supporting several key extensions. First, user-defined types, UDTs. This is a big one. You're no longer limited to the standard built-in data types like integer, varchar, or date. UDTs let you define your own customized, often complex data types.
Like creating your own building blocks.
Precisely. There are different kinds. You can create distinct data types. These let you specialize existing SQL types to enforce semantic correctness. For example, create distinct type US dollar as decimal 82 and create distinct type euro as decimal 8 and 2. Even though both are decimals, the database would prevent you from accidentally adding dollars and euros together without an explicit conversion. It adds a layer of type safety.
Preventing mistakes.
Yes. Then you have unnamed and named row types. These let you group a coherent set of standard data types into a new composite type. Think of defining an address row type that contains street address, varchar, zip code char, and city varchar. An employee table could then have a column named home address of type address. This allows for more structured, complex attributes within a table, meaning your tables are no longer strictly restricted to the first normal form requirement of having only atomic values in each cell. It offers more modeling flexibility.
You can have structured data inside a cell.
Kind of, yes. You can model things more naturally sometimes. There are also table data types, typed tables. These let you define the type of a table itself, much like defining a class in OO programming, which you can then use to instantiate multiple tables with the exact same structure and potentially associated methods. Second major feature, inheritance. RDBMS allow you to define table hierarchies. Just like with EAR or UML, you could have an employee super table and then define engineer and manager tables that inherit columns from employee. Queries on the super table, like select from employee, could automatically retrieve data from both the employee table and its subtables, engineer manager, or you could query only employee to exclude the subtables. It gives you precise control over hierarchical data.
Handling hierarchies directly in SQL.
Yes. Third, behavior. RDBMSs can store executable code or behavior directly in the database. This includes triggers. These are pieces of code automatically executed in response to specific database events, like insert, update, delete on a table. For our Sober Taxi app, you could create an after insert on ride trigger that automatically calculates the duration attribute by subtracting pickup date time from drop off date time, ensuring that calculation is always done consistently whenever a new ride record is inserted. Stored procedures and user-defined functions, UDFs. These allow you to encapsulate complex business logic or calculations within the database itself. Applications can then call these procedures or functions instead of embedding the logic themselves. This improves performance, logic runs closer to the data, enhances security, users might only have permission to execute the procedure, not access tables directly, and promotes reusability.
Moving logic into the database.
Exactly. And finally, recursive queries. These are incredibly powerful extensions to SQL, specifically designed for navigating hierarchical or graph-like data structures stored in tables. A classic example is an employee reporting structure, where each employee record might have a manager and pointing to another employee record. A recursive query could easily find all direct and indirect subordinates of a given manager, traversing the hierarchy efficiently. This is very difficult to do with standard SQL.
Okay, so if we connect this to the bigger picture again, RDBMSs seem to offer a compelling middle ground, blending the robustness of relational systems with the flexibility of object features. How does understanding these capabilities impact someone's career in information systems today? Are these features widely used?
Yes, these features are quite widely used, especially in enterprise-level databases from major vendors like Oracle, IBM, DB2, Microsoft, SQL Server, and PostgreSQL. Understanding them means you have greater flexibility in modeling complex real-world data more naturally and accurately. This often leads to more powerful, more efficient, and easier to maintain applications. For your career, this translates directly into opportunities in designing and managing sophisticated databases that can handle the intricate relationships and behaviors common in modern business data. Being able to leverage UDTs, inheritance, triggers, stored procedures, and recursive queries allows you to build more expressive and capable information systems using these robust, widely deployed platforms. It definitely positions you for more advanced architectural and database design roles.
So knowing RDBMS features opens up ways to tackle complexity within established systems. That makes sense. But then, as data volumes just exploded with the internet, social media, IoT devices, and as internet-scale applications became common, even these enhanced relational databases started facing a new kind of challenge, right? Remember our hypothetical sober self-driving taxi company. They're considering different scenarios to handle massive growth. They might be exploring NoSQL solutions because their traditional RDBMS, even an object-relational one, might struggle to scale effectively and handle, say, the real-time ingestion and querying of geolocation data from a vast fleet of cars constantly. This brings us to the fascinating and, frankly, sometimes confusing NoSQL movement.
Indeed. You've hit on the key drivers. Relational database management systems, RDBMSs, including ORID BBMSs, fundamentally prioritize strong consistency, typically by enforcing those ACD properties rigorously. This strong consistency, while absolutely crucial for ensuring data integrity in many applications, like banking, can introduce significant overhead and potentially hamper performance and scalability, especially in highly distributed environments where data needs to be spread across hundreds or thousands of servers. The NoSQL movement, which really means not only SQL more than no SQL at all, describes a whole range of diverse non-relational database management systems that emerge specifically to address these limitations. They generally focus on achieving massive horizontal scalability, adding more machines, and greater flexibility, handling varied or rapidly changing data structures in these large-scale distributed settings. But this often comes with a trade-off, usually involving weaker consistency guarantees compared to traditional RDBMSs.
Okay, scalability is a big driver. You mentioned horizontal versus vertical scaling. Can you elaborate on why RDBMSs struggle more with horizontal scaling?
Sure. When we talk about scaling databases, vertical scaling means making a single server more powerful, adding more RAM, faster CPUs, better disks. RDBMSs are generally very good at scaling vertically, up to a certain point. Horizontal scaling, sometimes called scaling out, means adding more servers or nodes to a cluster and distributing the data and workload across them. RDBMSs traditionally struggle with massive horizontal scaling, primarily because of their strong consistency guarantees, ACID. Ensuring that every node in a large cluster has the exact same perfectly consistent view of the data at all times, especially during high volumes of updates, requires complex and often slow synchronization mechanisms, like two-phase commit protocols. This coordination overhead becomes a bottleneck as you add more and more machines.
So maintaining perfect consistency across many machines gets really hard really fast.
Exactly. And this is where the famous CK-pi theorem comes into play. It's a fundamental principle in distributed systems, first conjectured by Eric Brewer. It states that any distributed data store, like a database spread across multiple machines, can only simultaneously guarantee two out of the following three properties. Consistency. Every read receives the most recent write or an error. All nodes see the same data at the same time. Availability. Every request receives a non-error response without guarantee that it contains the most recent write. The system is always operational. Partition tolerance. The system continues to operate despite an arbitrary number of messages being dropped or delayed by the network between nodes. Basically, it handles network splits.
Consistency, availability, partition tolerance. Pick two. Why can't we just have all three? It sounds like you'd always want all of them.
It does sound ideal, but think about what happens during a network partition, say. The network connection between two data centers holding parts of your database goes down. If you want to maintain perfect consistency, you might have to stop accepting writes in the partition that can't communicate because it can't guarantee those writes are seen by the other side. This sacrifices availability A. If, on the other hand, you prioritize availability A during the partition, you might allow both sides to continue accepting writes independently. The system stays up. But now, the data on the two sides might diverge, sacrificing strong consistency. Once the partition heals, you'll have to reconcile the conflicting changes. Since network partitions are a fact of life in large distributed systems, the CAP theorem essentially forces a choice between strong consistency and high availability during those partitions.
Okay, so you have to trade one off when a network breaks.
Precisely. Traditional RDBMSs typically prioritize consistency, often C and A within a single non-partition system, or C and P if distributed but potentially sacrificing A during partitions. Most NoSQL databases, designed for web scale, often choose to prioritize availability and partition tolerance, A and P, which means they often sacrifice immediate strong consistency across all nodes.
And that leads to eventual consistency.
Exactly. Instead of the strict ACID guarantees, many NoSQL databases follow the BASE principle. It stands for, basically, available. The system guarantees availability, in the sense of the CAP theorem. Soft state. The state of the system may change over time, even without input, because of eventual consistency, eventually consistent. The system will eventually become consistent once all inputs cease. Data changes will propagate to all nodes, but not necessarily instantaneously. This eventual consistency is a key characteristic and a fundamental trade-off made by many NoSQL systems to achieve higher availability and scalability. For some applications, like social media feeds or product catalogs, a slight delay in consistency is perfectly acceptable. For others, like financial transactions, it's usually not.
Okay, base versus ACID, a different set of priorities. So it's clear NoSQL isn't a monolithic thing. It's definitely not a one-size-fits-all solution. Let's explore the different flavors. What are the main categories of NoSQL databases?
You're absolutely right. It's a wondrously diverse landscape, and different types are optimized for very different use cases. The main categories include, first, key value stores. These are perhaps the simplest type. They store data primarily as a collection of unique keys, each associated with an arbitrary value. Think of a giant hash map or dictionary. They offer incredibly fast reads and writes for simple lookups by key. A classic example often used for caching is memcached, or more persistent stores like Redis or React. In a distributed environment, they use techniques like distributed hash tables to figure out which server should store which key, membership protocols to keep track of which servers are up or down, and replication, storing copies of data on multiple servers, for fault tolerance. Our sober company might use a key value store for very fast lookups of driver status or caching frequently accessed customer profile details.
Super simple, super fast lookups. Got it.
Second, document stores. These store data in semi-structured documents, often using formats like JSON, JavaScript Object Notation, or BSON, binary JSON, or sometimes XML. Each document is typically a collection of key value pairs, but the values can themselves be complex nested structures or arrays. Think of storing a whole blog post with its title, author, content, tags, and comments all within a single document. MongoDB is a very popular example. Couchbase is another. They are great for applications with flexible or evolving schemas where each document might have slightly different fields. However, complex relational queries, like finding all books written by authors older than 50 who live in a specific state, might need to be resolved by hand at the application code level, potentially involving multiple queries or data retrieval, followed by client-side filtering.
More flexibility in structure, maybe harder joins.
Often, yes. Document stores frequently leverage frameworks like MapReduce for performing large-scale data aggregation or analysis across many documents. MapReduce works in two phases. The map phase processes input data, example, documents, and emits intermediate key value pairs. The reduce phase then takes all pairs with the same intermediate key and aggregates them somehow, e.g. summing counts, calculating averages. For example, if you wanted to calculate the average page count per book genre across millions of book documents, the map function might read each book document and emit genre, page count 1. The reduce function would then receive all pairs for a given genre, sum up the total page counts, sum up the ones to get the total number of books, and finally compute the average. It's a powerful paradigm for distributed processing.
MapReduce for big data crunching in document stores. Okay, what's next?
Third, graph databases. These are fundamentally different. You could almost call them hyper-relational because they focus intensely on the relationships between data entities. They model data as nodes, entities, and edges, relationships connecting the nodes. Both nodes and edges can have properties, attributes. They are ideal for data sets where the connections and paths between items are just as important or even more important than the items themselves. Think social networks, who is friends with whom, who liked what post. Recommendation engines, users who bought this also bought that. Fraud detection, linking seemingly unrelated accounts through shared information. Or location-based services, finding routes, points of interest nearby.
All about the connections.
Exactly. Neo4j is a leading example, and it uses a specific query language called Cypher, which is designed to express graph traversals naturally. Instead of writing complex SQL join clauses to navigate relationships across multiple tables, you write patterns that describe the traversal. For example, finding all books written by a particular author might involve a simple pattern match, like match A, author name, wrote, B, book, return, B, title. Or a more complex recommendation query, like finding humor books that friends of Bart Bason's liked but Bart hasn't seen yet, might look something like match me, reader name, friends with, friend liked, B, book. Has a genre, G, genre name, humor, liked, B, return distinct friend.name, B, title. It's very expressive for relationship-based queries.
Cypher sounds powerful for that kind of problem. Any other main types?
The fourth major category often mentioned is column-oriented databases, or wide column stores. Examples include Cassandra and HBase. Unlike traditional row-oriented databases that store all data for a row together, these databases store data by columns. All values for column A are stored together, then all values for column B, and so on. This structure is highly optimized for analytical queries that typically only need to read a few columns from a massive number of rows. For example, calculating the average sales price across millions of transactions. They can read just the necessary columns very efficiently without having to load all the other data for each row. They're often used in big data analytics and data warehousing scenarios.
Optimized for reading columns, great for analytics. Okay, that's a diverse landscape. Key value, document, graph, column-oriented. So for a dynamic business like our sober taxi company facing growth and complex data needs, or for someone looking to specialize in big data or system architecture, how do you make the right technology choices given all these different NoSQL options alongside traditional RDBMSs?
That's the million-dollar question, isn't it? Connecting this back to the bigger picture, the NoSQL movement provides a rich toolkit of diverse, specialized solutions designed to address challenges that traditional relational databases sometimes face, particularly around massive scale, high availability requirements, and handling flexible or unstructured data. It's not about NoSQL being inherently better than SQL or vice versa. It's about understanding the specific problem you're trying to solve and choosing the right tool for that job. For your career, this explosion of options means tremendous opportunities in areas like big data engineering, data science, cloud architecture, and designing highly scalable, resilient distributed systems. The ability to analyze a business problem, understand the data characteristics, volume, velocity, variety, structure, understand the required consistency and availability levels, ACID versus base cap trade-offs, and then choose the most appropriate database technology, whether that's a strongly consistent RDBMS for core financial transactions, a scalable document store for a product catalog, a graph database for fraud detection, or a key value store for session management. That ability is a hallmark of an advanced information systems professional and architect. It requires moving beyond knowing just one type of database and embracing a polyglot persistence mindset, using multiple data storage technologies within a larger system, chosen based on the specific needs of each component. That's a key skill for the future.
Polyglot persistence. Using the right tool for the right part of the job. That makes a lot of sense. It's about a broader toolkit. Now, we've talked a lot about storing and accessing data, whether it's relational or NoSQL. But there's a fundamental prerequisite we haven't fully unpacked yet. Data, no matter how much you have or how fast you can access it, is only really valuable if it's good data, right? You can have petabytes of information, terabytes flowing in every second. But if it's inaccurate, incomplete, or inconsistent, it's essentially useless or even harmful for making informed decisions. So this raises a really important question. What does good data actually mean in a practical business context?
That is absolutely fundamental. Data quality DQ is paramount. It's often defined simply as the fitness of data for its intended use. Is the data good enough to do what you need to do with it? And good enough is typically assessed across several key dimensions. These dimensions help us quantify and manage data quality systematically. First, accuracy, probably the one people think of most often. Are the data values correct and precise? For example, is a customer's birth date recorded as 02271975 actually correct, or should it be 02719766? Is the format even correct? Is that February 27th or July 2nd if you have international users? Accuracy issues are often symptoms of other underlying DQ problems, like how data is represented or if it's up to date.
Correctness, got it.
Second, completeness. Are all the necessary data values actually present? Are there missing values, often represented as NLL in databases? Sometimes missing values are okay, or even provide useful information about user behavior. Favorably, someone didn't fill in an optional field. But often, missing critical data renders a record unusable for certain analyses or operations.
Are the blanks filled in?
Essentially, yes. Third, consistency. This has a couple of facets. Do different data elements that represent the same real-world concept agree with each other? For example, if you have both a city name and a postal code for an address, are they consistent? Does the postal code actually exist in that city? Also, is the format consistent across the data set or across different systems? Is it always New York, or sometimes NY or NY? Inconsistencies often arise when data is shared or integrated from multiple departments or legacy systems that had different standards.
Agreement and uniform representation.
Right. Fourth, timeliness. Is the data sufficiently up to date for the current business needs? An old customer address might be technically accurate for the past, but if it's not their current address, its value for mailing campaigns or deliveries is greatly diminished. Data decays over time.
Is it fresh enough?
Exactly. Fifth, accessibility. Is the data available when needed and easily retrievable by authorized users and systems? Data locked away in an inaccessible silo or in a format that's hard to process has low accessibility, regardless of its other qualities. And sixth, often overlapping with accessibility but distinct, is security. Is access to the data appropriately restricted to maintain confidentiality and integrity? Data that's accurate but exposed to unauthorized access has a major quality flaw from a security perspective.
Accuracy, completeness, consistency, timeliness, accessibility, security. That's a really comprehensive list of qualities. It highlights that good data is multifaceted. But who are the champions within an organization responsible for ensuring data meets these quality standards? And what do they actually do on a day-to-day basis to maintain it? It sounds like a constant battle.
It can be. Maintaining high data quality is a continuous effort that involves various specialized roles working together within a broader data management or data governance framework. You have the information architect, who designs the overall data strategy and blueprints. The database designer creates the conceptual and logical data models, which is a first step towards quality. The data owner is typically a business leader ultimately responsible for a specific data set, like customer data or product data. But the real frontline DQ experts are often the data stewards. These individuals, often embedded within business units but with specific DQ responsibilities, are tasked with understanding, measuring, and improving the quality of specific data assets. They perform regular data quality checks, maybe using profiling tools. They calculate DQ indicators or metrics based on those dimensions we discussed. They investigate the root causes of poor data quality. Is it a faulty entry screen, a bad data feed, a lack of training?
So they're the detectives and the fixers.
They are. But crucially, their focus should ideally be on designing preventative measures, not just corrective ones. It's far more effective and cost-efficient to prevent bad data from entering the system in the first place. This might involve working with application developers to make certain fields mandatory, using drop-down lists instead of free text fields where possible, implementing real-time validation checks against reference data, like ensuring a state code is valid, or improving user training.
Prevention over cure.
Absolutely. Then you have the database administrator, DBA, who manages the physical database infrastructure and ensures its performance and availability, which indirectly supports DQ. And the data scientist, who extracts insights and builds models, but whose work is fundamentally dependent on the quality of the input data. Garbage in, garbage out is very real in data science. For your career, regardless of your specific role in IT or data, understanding the principles of data quality and championing DQ initiatives is a significant differentiator. It ensures that the insights derived from data are reliable, that business decisions are based on solid foundations, and that the systems you build, manage, or use are trusted and effective. Poor data quality undermines everything else.
Absolutely critical foundation. Okay, so we need good quality data. We've also talked about conceptual models, the blueprint, and logical models like relational tables. But beneath all that abstract design, the data has to physically live somewhere, right, on actual hardware. What goes into designing that somewhere? How do we translate the logical design into an efficient physical implementation that ensures both performance and reliability?
Right. This is where the rubber meets the road. Physical database design is all about how the logical database concepts, tables, rows, columns, indexes are actually realized as stored records, physical files, and ultimately bits and bytes and physical storage devices. It bridges the logical world with the hardware reality. There are several layers to consider. First, the stored hardware itself. This involves understanding the characteristics of devices like traditional hard disk drives, HDDs, with their spinning platters and moving read-write heads, and newer solid-state drives, SSDs, which use flash memory and have no moving parts, offering much faster random access. We need to understand how data is organized on these disks, into tracks, sectors, the smallest physically adjustable unit on an HDD, and how the operating system and DBMS group these into disk blocks, or pages, which are the actual units of data transfer between disk and memory. Block size is an important tuning parameter.
Knowing the characteristics of the underlying storage.
Yes. Then, critically for performance and reliability, comes RAID, redundant array of inexpensive disks. RAID isn't a specific product, but a set of techniques for combining multiple physical disk drives into one logical unit. The goals are typically to improve performance by reading and writing across multiple disks in parallel, and/or to provide data redundancy to protect against individual disk failures. Different RAID levels offer different trade-offs. RAID 0, striping. Data is split, striped across multiple disks. This improves performance significantly because multiple disks work in parallel. But it offers zero redundancy. If any one disk in the array fails, all data is lost. High speed, high risk.
Okay, maybe not ideal for critical data.
Generally not, unless performance is the absolute only concern and you have other backup strategies. RAID 1, mirroring. This provides full data redundancy by writing identical copies of the data onto two or more disks simultaneously. If one disk fails, the others still have the complete data, so the system keeps running. It offers excellent read performance, can read from any mirror, but write performance can be slightly slower, have to write to all mirrors, and the storage cost is high because you need at least double the disk space. High safety, high cost.
The safe but expensive option.
Kind of. Then there are levels that use parity for redundancy, which is more space efficient than mirroring. RAID 3, bit-level striping with dedicated parity disk. Data is striped at the bit or byte level across multiple disks, and one entire disk is dedicated solely to storing parity information. Parity allows the system to reconstruct the data from a failed disk using the data on the remaining disks, plus the parity information. It offers good read performance, but the dedicated parity disk can become a bottleneck during writes, as every write requires updating the parity disk. RAID 5, block-level striping with distributed parity. This is very popular in enterprise systems. Data is striped in larger blocks across multiple disks, and the parity information is distributed across all the disks in the array, rather than being on a single dedicated disk. This avoids the write bottleneck of RAID 3 because parity writes are spread out. It offers a good balance of performance, both read and write, redundancy, and storage efficiency.
RAID 5 seems like a common sweet spot.
It often is, although other levels like RAID 6, which uses double distributed parity for even more redundancy, and RAID 10, a combination of striping and mirroring, are also widely used depending on specific needs. Understanding RAID levels is crucial for DBAs and system architects choosing storage configurations. Beyond the hardware and RAID, we need to consider how individual records are organized within those disk blocks. Record organization. One way is relative location. Data items within a record are identified by their position or offset. This is most efficient for structured data with fixed-length fields, like in traditional relational tables. Another is embedded identification. For highly irregular record structures, maybe with many optional or variable length attributes, each data item within the record might be preceded by an identifier for its attribute type. For example, SSN 123-456, name Smith address 1 mainsent. This is similar to how semi-structured data like XML or JSON often organize information within a document. More flexible, but uses more space. We also use pointers and lists within or between records, especially for handling multi-valued attributes like storing multiple phone numbers for one person, or for managing overflow when a record becomes too large to fit in its original block. Pointers link related pieces of data together.
How the bits are arranged within a record, and then how are records arranged within a file.
Right, that's file organization. This defines how records are physically arranged within a database file on disk, and it heavily influences how efficiently you can access them. Heap files. Records are stored in no particular order, usually just appended to the end of the file as they arrive. Insertions are very fast, but finding a specific record requires scanning the entire file, unless there's a separate index. Good for bulk loading, bad for retrieval. Sequential files. Records are stored in a fixed physical sequence based on the value of some key field, AG, sorted by employee ID. This is very efficient for processing records sequentially in that key order, but inserting or deleting records can be slow because it might require shifting other records to maintain the sequence. Index sequential files, like ISAM, these try to combine the benefits of sequential files, efficient sequential processing, with faster direct access. They keep the records mostly sequential, but also maintain an index, like a B tree, to allow direct lookup of records by key without scanning the whole file, hashing, or direct files. This uses a hash function, a mathematical function that converts a record's key value directly into a disk block address. This provides potentially very fast direct access to a record given its key, ideally just one disk grid. However, you need a good hash function to distribute records evenly, and you need mechanisms like chaining, using pointers to link records that hash to the same address called collisions, or secondary hashing to handle overflow when multiple keys map to the same address. Hashing is great for exact key lookups, but usually poor for range queries or sequential processing.
Different ways to lay out the file for different access needs. Heap, sequential, indexed, hashed.
Exactly. And finally, related to physical design is how join implementations work. We talked about SQL joins being fundamental. Since they often involve comparing data from multiple large tables, they can be one of the most time-consuming operations in a database. The DBMS Query Optimizer chooses a physical join algorithm based on table sizes, available indexes, and other factors. Nested loop join, This is the simplest, conceptually. For every row in the outer table, it scans the entire inner table looking for matches on the join condition. It can be very slow if the inner table is large and unindexed. Sort, merge, join. This first sorts both tables based on the join attribute. Then it merges the two sorted tables, efficiently finding matching rows like merging two sorted lists. Good if the tables are already sorted or need to be sorted for other reasons anyway. Hash join. This is often very efficient for large unsorted tables. It uses hashing. It first builds a hash table in memory based on the join attribute from the smaller build table. Then it scans the larger probe table, hashes its join attribute values, and looks them up in the hash table to find matches quickly. Requires sufficient memory for the hash table.
Wow, okay. So the optimizer picks between nested loop, sort merge, hash join, and maybe others, based on what it thinks will be fastest. This deep dive into physical design really shows how raw data becomes a highly optimized performing system. It's clear this level of understanding isn't just for specialized DBAs. It's key knowledge for any high-impact IT professional who needs to design, manage, or even just effectively use systems that are fast, reliable, and cost-effective. It connects a logical model all the way down to the disk ladders and join algorithms.
Absolutely. Now, building on that theme of reliability in today's always-on 24/7 digital world, downtime is just not an option for most critical businesses. Think about an online retailer during a major sale, a global financial trading system, or a critical healthcare system managing patient records. Even a few minutes of outage can mean massive financial losses, reputational damage, or, in some cases, put lives at risk. So how do we ensure that our vital data and the systems that depend on it are continuously available? How do we protect against everything from a single disk failure to a major disaster like a fire or flood taking out a whole data center?
This is a paramount concern, and it leads directly to discussions about high availability, HA, and disaster recovery, DR. And the starting point for any serious HADR strategy is defining two critical business metrics: your recovery point objective, RPO, and your recovery time objective, RTO.
RPO and RTO. Heard those acronyms. Can you break them down?
Sure. RPO, recovery point objective. This defines the maximum acceptable amount of data loss, measured in time back from the point of failure. For example, if your RPO is 1 hour, it means your business can tolerate losing up to 1 hour's worth of data that was created or modified just before the disaster struck. This dictates how frequently you need to back up or replicate your data. An RPO of 0 means absolutely no data loss is acceptable. RTO, recovery time objective. This defines the maximum acceptable amount of time that a system or application can be down after a disaster or failure occurs before it must be restored to operational status. For example, an RTO of 4 hours means the business requires the system to be back up and running within 4 hours of the outage. An RTO of near 0 implies almost instantaneous failover is required.
So RPO is about how much data you can lose. RTO is about how much time you can be down.
Exactly. And these two objectives, RPO and RTO, are fundamentally business decisions, not purely technical ones. They dictate the level of investment required in HADR solutions. A global online shop might have near 0 RPO and RTO requirements because every second of downtime and any lost transaction data translates directly into huge financial losses and customer dissatisfaction. They'll invest heavily in sophisticated solutions. On the other hand, maybe a secondary school's internal administrative system might tolerate an RPO of 24 hours. For example, nightly backups are sufficient, and an RTO of, say, 8 hours. It's okay if it takes a business day to restore. Their investment will be significantly lower.
The business impact drives the technical requirements. Makes sense. So what are the common strategies used to meet these different RPO targets?
There's a spectrum of strategies, ranging from basic to highly sophisticated. At the simpler end, you might have manual failover. This involves having a standby server ready, perhaps with recently restored backups. If the primary system fails, manual intervention is needed to bring the standby online and switch users over. This results in a relatively high RTO because of the manual steps involved.
Simple, but slow recovery.
Right. Moving up, we have clustering. This involves multiple interconnected computer systems, nodes, working together, often appearing as a single system to users. Clustering serves two main purposes for HA. First, it can improve performance through parallelism, multiple nodes sharing the workload. Second, and crucially for HA, it provides automated failover. If one node in the cluster fails, due to hardware or software issues, its workload is automatically taken over by other healthy nodes in the cluster, ideally with minimal interruption to service. This significantly reduces RTO compared to manual failover. Clustering is also essential for avoiding planned downtime, for instance, allowing rolling upgrades where you upgrade nodes one at a time without taking the whole service offline.
Clustering for automatic failover and avoiding planned downtime. Good. But what about a whole data center disaster?
Exactly. Clustering typically happens within a single data center. For protection against larger-scale disasters, fire, flood, power outage affecting a whole site, you need remote data replication as part of a disaster tolerance strategy. This is especially critical for organizations with very stringent Arcordo requirements. It involves continuously replicating data from the primary data center to a secondary, geographically distant data center. There are two main modes: synchronous replication. Every write operation on the primary site must be successfully written and acknowledged by the remote site before the application receives confirmation. This guarantees zero data loss, RPO equals 0 if the primary site fails. However, it's very sensitive to network latency between the sites. The distance can significantly impact application performance because writes have to wait for the round-trip confirmation. Asynchronous replication. Writes are confirmed back to the application as soon as they complete on the primary site. The replication to the remote site happens shortly after, but independently. This is much less sensitive to network latency and distance, allowing for sites further apart. However, it comes with the potential for minor data loss, RPO 0. Any data written to the primary site just before it fails might not have made it to the remote site yet.
Synchronous for zero data loss but distance limited. Asynchronous for longer distances but potential small data loss. Trade-offs again?
Always trade-offs. And you can combine these concepts. A stretched cluster, or metro cluster, essentially extends a high-availability cluster across two or more geographically separated sites, often using synchronous replication between them. Specialized cluster management software handles automated failover and potentially load balancing between the sites, aiming for very low RTO and RPO across sites.
Taking clustering across data centers, that sounds robust.
It is, but complex and expensive. Finally, it's important to remember transaction recovery. It's not just about replicating the data bytes. The database system, DBMS, must ensure transactional integrity, those ACD properties, even during a failover or disaster recovery scenario. If a complex bank transfer involving multiple database updates is only partially completed when a disaster strikes and failover occurs, the DBMS's recovery mechanisms, using transaction logs, must ensure that the incomplete transaction is properly rolled back on the recovery site, leaving the database in a consistent state. You can't have money debited from one account but never credited to the other just because a failover happened mid-transaction.
Maintaining ACID even through disasters. Wow. Okay, this whole area of high availability and disaster recovery, it's clear that understanding these concepts, the Arcordo drivers, the different technologies like clustering and replication, this isn't just for specialized IT infrastructure folks. It's fundamental business continuity planning and risk management. It feels like a critical area of knowledge for any leader involved with information systems, as it directly impacts the organization's resilience and its variability to operate reliably in an increasingly unpredictable digital world.
Couldn't agree more. It's absolutely strategic.
All right. So far, we spent a lot of time talking about structured data, the kind that fits neatly into relational tables, and even how object relational systems handle more complex types within that structure. But as we touched on with Noah Naiskel, a huge part of the digital world today runs on what's often called semi-structured data. Think about the content of web pages, HTML, configuration files, data exchanged between applications, sensor readings from IoT devices. How do we handle data that doesn't necessarily fit a rigid, predefined schema, especially when different applications and systems need to exchange and understand it, often across networks?
That's a great transition because this is exactly where formats like XML and JSON become absolutely essential. They are the dominant standards for representing and exchanging semi-structured data. Let's start with XML, Extensible Markup Language. Many people are familiar with HTML, which uses tags like P for paragraph, H1 for heading, to define the layout or presentation of content on a web page. XML also uses tags, but with a crucial difference. In XML, the tags are self-defined by the creator of the document, and they're intended to describe the structure and meaning of the data, not just its layout. This makes XML documents inherently self-descriptive. For example, you might have author Bart Basins author or product name widget name price 19.99 price product. The tags tell you what the data represents.
Tags define meaning, not just looks.
Exactly. For an XML document to be considered well-formed, it just needs to follow some basic syntax rules, like tags must be properly nested, every start tag needs a corresponding end tag, etc. But you can go further and define a formal structure for your XML documents using a schema. There are a couple of ways to do this. Older DTDs, document type definitions, provide a basic way to define allowed elements and their nesting. But much more powerful and widely used is XML schema, often using the .xsd extension. XML schema is semantically much richer. It allows you to specify not just the allowed elements and attributes, but also their data types, like xs.string, xs.integer, xs.float, xs.date, cardinality constraints, how many times an element can appear, e.g. min occurs, max occurs, key relationships, and much more. It's very much like defining a schema for a database, but for XML documents.
So XML schema brings database-like structure definition to XML.
Precisely. Our sober taxi company, for instance, might use an XML schema to rigorously define the required structure for electronic accident reports. The schema could specify elements for date, time, location, perhaps with mandatory GPS coordinates using specific numeric types, and details about the actors involved, drivers, pedestrians, cyclists, maybe with attributes like injured, Boolean, or vehicle type, ANUM. This ensures all reports conform to a standard structure for automated processing.
Okay, and how do we store and query this XML data?
Storing XML can be done in a few ways. Sometimes it's stored as just a black box, a binary large object, BLOB, or character large object, CLOB, inside a traditional relational database column. Simple, but hard to query the contents directly using SQL. Alternatively, the XML can be shredded, broken down, and mapped into relational tables. This allows querying with SQL, but can be complex to set up and maintain, especially if the XML structure changes. Many databases now also offer native XML data types and specialized querying capabilities. You can query XML documents using languages like XPath. This is a language for navigating within an XML document, selecting specific nodes, elements, or attributes based on their path or properties. For example, doc myreport.xml at report actor at injured true might select all actor elements within the report that have an injured attribute set to true, xquery. This is a more powerful functional query language specifically designed for querying collections of XML data. It builds on XPath and adds capabilities for transforming, joining, and restructuring XML data, similar in power to SQL but for XML.
XPath for navigating, XQuery for complex querying and transformation. Got it. What about semantic search?
Good point. Beyond just finding elements based on structure, there's a whole area related to the semantic web, aiming to make data understandable not just by humans, but also by machines in terms of its meaning and relationships. RDF, Resource Description Framework, is a W3C standard for representing information about resources using subject-predicate-object triples. Think of simple statements like Bart Basin subject, likes predicate, Meneghetti white wine object. RDF allows you to build interconnected graphs of knowledge. ClearRQL is the standard query language for querying these RDF graphs. It allows you to ask highly complex semantic questions that go beyond simple keyword or structural matching. For example, you might query for all spicy ruby-colored red wines with a round texture that pair well with cheese, assuming the underlying RDF graph contains that kind of rich semantic information. This is critical for the future of intelligent search and linked data.
RDF and Sparkle for querying meaning and relationships. Fascinating. Now, what about JSON? It seems to be everywhere, especially in web development.
Yes, JSON JavaScript object notation has become incredibly popular, often seen as a lighter-weight, less verbose alternative to XML, particularly for data exchange between web servers and JavaScript running in web browsers, though its use is much broader now. It's designed to be easy for humans to read and write, and easy for machines to parse and generate. It models data hierarchically using key-value pairs like objects or dictionaries, and ordered lists, arrays. Like XML, it's semi-structured, and you can define its structure formally using JSON schema. Key differences from XML. JSON is not a markup language in the same way, no start and tags for data. It's primarily a data serialization format. It doesn't have built-in support for namespaces or attributes in the same way XML does. It's generally considered simpler and often results in smaller message sizes, which is advantageous for network transmission.
Lighter, simpler, good for web APIs. Okay, it's clear how both XML and JSON are essential formats for allowing different systems, potentially built with different technologies, to understand and exchange data. How does this connect directly to web services, which are fundamentally about enabling that system-to-system communication?
You've nailed the connection. XML and JSON are the lingua franca, the common languages, used for the actual data payload within modern application integration, particularly for web services. They provide the standardized formats needed for diverse systems to exchange structured or semi-structured information reliably across networks, usually the internet. They are the content being sent back and forth.
The data formats that web services use to talk.
Got it.
Okay, let's bring it all together now. We have all this data, potentially in different formats, relational object, relational, NoSQL, XML, JSON. How do different systems and applications actually communicate with each other across the digital landscape, often over the internet, to get things done? We need a way for them to call each other, exchange this data, and coordinate actions. This sounds like the domain of web services.
Precisely. This falls under the umbrella of Enterprise Application Integration, EAI, which is the broad set of activities, technologies, and architectures aimed at making different applications within an enterprise, like ERP, supply chain management, CRM systems, or even between different enterprises, B2B integration, work together seamlessly. Web services provide a standardized, technology-agnostic way for software components, or entire applications, to be published, discovered, and invoked remotely, typically over standard web protocols like HTTP. They allow applications to interact programmatically regardless of the programming language they're written in or the platform they run on. There are two main architectural styles or protocols commonly associated with web services. First, SOAP, originally Simple Object Access Protocol. This is a mature XML-based messaging protocol. It defines a standardized envelope structure for sending messages. A SOP message typically contains an optional header section for metadata like security or transaction information, and a compulsory body section, which contains the actual application-specific payload encoded in XML. SOP is designed to be extensible. You can add features via headers, neutral. It can theoretically travel over different protocols like HTTP, SMTP, etc., though HTTP is most common, and independent of programming languages. For example, a SOAP message could be structured to call a get_quote web service, passing a stock symbol in the XML body, and receive the stock quote back in another SOP message.
So SOP is XML-based, standardized envelope, quite formal.
Yes, very much so. It's often associated with more formal contracts and enterprise-level integrations. Despite its versatility, SOP can be quite verbose due to XML, and is sometimes perceived as heavy or complex to work with compared to alternatives. Associated with SOP is WSDL, Web Services Description Language. This is another XML-based language used to describe the capabilities of a SOP-based web service. A WSDL file acts like a formal contract or a user manual. It specifies exactly what operations the service offers, what input messages, parameters each operation expects, what output messages, return values it produces, and how to actually connect to the service, its endpoint address. Tools can often use WSDL files to automatically generate the code needed to interact with the web service.
WSDL is the instruction manual for the SOAP service.
Okay.
Yeah. What's the other main style?
The other major style, which gained enormous popularity, especially with the rise of web APIs for mobile and web applications, is REST, Representational State Transfer. REST isn't a specific protocol like SOAP, but rather an architectural style or set of principles for designing networked applications, primarily built directly on top of the existing HTTP protocol. Instead of defining its own envelope structure, REST embraces HTTP. It uses standard HTTP methods, verbs, for operations. Get to retrieve data, post to create new data, put to update existing data, and delete to remove data. Resources, like users, products, orders, are identified by URLs. REST services typically exchange data using simpler formats, most commonly JSON, although XML or other formats can also be used. REST is generally considered lighter and simpler than SOAP, often resulting in less overhead and easier integration, especially from web browsers using JavaScript. The concept of API-first development, where designing the API is a primary step, is strongly associated with REST. Many modern web companies, like social networks, cloud providers, expose their functionalities through RESTful APIs.
REST leverages HTTP directly, often uses JSON, seen as lighter. But SOAP is still around.
Oh, absolutely. While REST is hugely popular for public-facing APIs and web mobile development, SOAP remains widely used in many enterprise environments, particularly for internal system-to-system integration, or where more robust features defined in the WS standards, like advanced security or reliable messaging, are required. It's often a case of choosing the right approach based on the specific requirements for formality, features, and performance.
So REST versus SOAP is another right tool for the job situation. If we connect this to the bigger picture one last time, these web service technologies, SOAP and REST using XML and JSON, are really the fundamental glue enabling our incredibly hyper-connected digital world. They allow everything from your mobile banking app to talk to the bank's mainframe systems, to different cloud services integrating with each other, to complex enterprise workflows spanning multiple applications. They make interoperability possible.
Absolutely. And web service technology also has a profound impact on how applications interact with databases. A web service often acts as an intermediary or facade. It might receive a request, say a REST call to get customer details, then query an underlying database using SQL or another mechanism to retrieve the information, format the results, perhaps as JSON, and send it back to the caller. Or sometimes, database functionality itself can be exposed directly as a web service. For example, a stored procedure in an object relational database could potentially be wrapped with a WSDL interface and published as a SOAP web service. This would allow other authorized applications to invoke that specific piece of database logic simply by sending the appropriate SOAP message without needing direct database connectivity themselves. The database could even use features like SQL XML or built-in JSON functions to format the results directly into the required format before returning them through the web service layer. Understanding these integration points, how data flows from databases, gets processed or exposed through web services using standard protocols and formats, and is consumed by various applications is absolutely crucial for anyone designing, developing, or managing modern, interconnected information systems. It's the plumbing of digital business.
That's a great way to put it, the plumbing of digital business. Okay, what a journey. We've really taken a deep dive today into the foundational and also the cutting-edge world of information systems. We started with the core, how database management systems are architected internally. We explored the art and science of data modeling using ER, and UML diagrams. We got a handle on the power and ubiquity of SQL for relational databases, including normalization. Then we navigated the evolution beyond purely relational, looking at object-oriented and object-relational databases, and then the diverse landscape of NoSQL solutions, tackling challenges of scale and flexibility, understanding concepts like CAP and base. We also uncovered the absolutely critical importance of data quality, what it means and who ensures it. We peered into the physical reality of storage with RAID and file organization, and the vital strategies for high availability, disaster recovery, understanding RPO and RTO. And finally, we saw how XML, JSON, and web services like SOAP and REST act as the essential glue connecting our digital world. Our mission today was to equip you with the essential knowledge to truly navigate and hopefully lead in this ever-evolving information systems landscape. Remember that bold question I asked right at the beginning about becoming a skilled navigator of that vast ocean of data. Well, after this deep dive, you should feel like you have a much more comprehensive map and a pretty reliable compass.
Definitely. The insights we've discussed today, they aren't just abstract academic concepts. They're the absolute bedrock of the modern digital economy. And the demand for professionals who can not only understand, but also skillfully navigate, design, optimize, and lead the development and management of these complex systems, well, it's enormous and constantly growing. We need information architects, database designers and administrators, data engineers, data scientists, security specialists, and strategic IT leaders who grasp these principles deeply. Mastering these fundamentals is absolutely crucial if you're looking to secure strategic IT positions and make a real, lasting imprint in today's fiercely competitive business arena. The ability to understand data from its core principles, to design efficient and scalable systems that ensure data quality and integrity, and to facilitate that seamless communication between applications using standards like web services. That combination positions you as an incredibly valuable asset in any organization striving for digital excellence and innovation.
That really highlights the opportunity. But it also raises an important practical question. For our listeners, especially students or early career folks inspired by this, where can they gain these essential skills and the credentials needed to truly elevate their expertise and make themselves stand out in the job market?
That's a vital question. For those aspiring to become leaders in the IT field or wanting to deepen their technical and strategic understanding, I wholeheartedly encourage exploring specialized graduate programs designed to provide this comprehensive, real-world focused knowledge. For instance, the Master of Science in Information Systems program offered at Tarleton State University's Dr. Sam Pack College of Business is a fantastic example. It's AACSB-accredited, a hallmark of quality in business education, and it's specifically crafted to prepare graduates for significant success and leadership roles in this digital era.
Okay, tell us a bit more about the Tarleton MSIS program. What makes it stand out?
Well, a few key things. First, it's a fully online program. This offers tremendous convenience and flexibility, allowing students to seamlessly integrate their studies with their existing professional work, academic background, or personal obligations. You can really shape your educational journey around your own schedule, which is huge for working professionals. Coursework is available year-round, and they have rolling admissions, making it accessible. Second, the curriculum is designed to establish a solid foundational groundwork in all key areas of information systems through required core coursework, like the BCIS 5311, Managing Information Systems course. Importantly, it welcomes students from diverse academic backgrounds. You don't necessarily need a tech undergraduate degree. Whether you come from business, science, liberal arts, or technology, the program ensures you build the necessary foundation for advanced studies and future career success. Third, beyond that strong core, there's a rich array of elective courses. This allows students to tailor the program significantly to fit their specific personal interests and professional goals. You can choose electives to specialize in areas that directly align with your career aspirations, whether that's more towards data analytics, cybersecurity, product management, or IT strategy. It equips you with targeted expertise. Think of it as preparing you for specialized IS roles in the same way an undergraduate business degree prepares you for a general MBA. While other excellent programs certainly exist out there, you mentioned WGU's online master's options in computer science or data analytics, which also offer flexibility and integrate industry certifications. What's particularly compelling about Tarleton's MSIS, being housed within the AACSB-accredited Dr. Sam Pack College of Business, is its focused approach blending deep technical IS knowledge with a strong business and strategic perspective. It's explicitly aimed at preparing graduates not just for technical roles, but for strategic IS leadership. You gain those critical IT skills needed for the future, but with a clear pathway towards securing strategic positions and leaving that lasting imprint we talked about.
That focus on strategic leadership within a business context sounds really valuable. It's truly inspiring how programs like Tarleton's MSIS are tailored to help individuals take ownership of their career path and embrace these exciting high-demand opportunities for growth in the information systems field. Okay, let's wrap up this deep dive. We've covered a massive amount of ground today. We journeyed through the intricate internal architecture of a DBMS, understanding all those crucial components like the query processor and transaction manager. We explored the art of data modeling with ER, and UML class diagrams. We mastered the fundamentals and power of SQL for relational data, including normalization. We navigated the evolving landscape beyond relational into object-oriented, object-relational, and the diverse world of NoSQL databases, tackling concepts like CAP and base. We underscored the absolute necessity of data quality, looked at physical storage using RAID and different file organizations, and grasped the critical importance of high availability and disaster recovery strategies with RPO and RTO. And we finished by seeing how XML, JSON, and web services, SOAP and REST, connect our digital world. Our mission was to equip you with that essential knowledge to navigate and lead. That initial question about being a skilled navigator of the data ocean. Hopefully you feel much better equipped now, with that mapping compass firmly in hand. If this deep dive sparked your curiosity, if it clarified some complex concepts, or if it added significant value to your understanding of information systems, maybe your own career journey, please take just a moment to hit that like, subscribe, and share button for the deep dive. Your support truly helps us spread this knowledge further and inspire more future IT business leaders.
And as you consider your next steps, perhaps reflecting on all these technologies and principles and thinking about the incredible possibilities within the field of information systems, ask yourself this. How will you leverage these deep insights to innovate, to lead, and to actively shape the future of technology within business? What specific challenge or opportunity in the digital world are you now feeling equipped and inspired to tackle?
Keep diving deep, keep learning, and keep building the future, one byte and one business solution at a time. This has been The Deep Dive, and we're proud to be powered by the Dr. Sam Pack College of Business at Tarleton State University. Until next time.